Hello, welcome. Yeah, so I have a super exciting video for you here on limits in multivariable calculus. Now, I already have videos on delta epsilon limit proofs in multivariable calculus, but that doesn't find you limit values. What that is, well, once you know the value of a limit, let's say here, and what will be our fourth example in this video, if we know that the limit is equal to 0, then the delta epsilon limit argument for multivariable calculus would allow you to prove that this limit is in fact equal to 0. In other words, it would allow you to prove this statement. So as far as delta epsilon limits in multivariable calculus, I have very well crafted videos on it, and so check out those videos, including, starting with the definition of the delta epsilon limit argument for multivariable functions, and then explaining why it makes sense and all that good stuff, and drawing parallels to what we did in single variable calculus and all that. Yeah? Okay. But this is super exciting because all the examples are well chosen, and I guarantee you that this is the best video on the topic. I haven't even really started getting onto it, but I feel okay. So, I actually couldn't find my other black mask, and this one is suffocating me. Okay, alright. Okay, too clowny. Let's get on with this. Yeah, so again, delta epsilon limits in multivariable calculus allow you to prove limit statements, but here we're trying to figure out what are the values, and I intentionally ordered them the way that I did. But to start the discussion, let's do this, which is, let's get some XYZ axes, and I suppose we have too much black on the board, so let's do it in a red marker. So fine, this is the Z axis, and so usually then the Y axis is the horizontal axis, so this is the Y axis, and then the X axis is usually drawn this way. So it's coming out of the whiteboard, the x-axis. And this thing, this sticky part, I don't know who thought that that was a brilliant idea. Well, I guess it was required, but okay, so again, Z here, and then Y here, and X here. And this is positive X coming out of the whiteboard, is positive X. And going to the right is positive Y, and positive Z is here. Okay, so let's consider the following curve. Well, if we considered Z is equal to X squared plus Y squared, yes, you can use this awesome free online tool called GeoGebra. They've got 3D graphing programs, and so you can graph it using GeoGebra. Insert. So the reason why this is easy to graph is because notice in this three-dimensional coordinate system, if I make y equal to 0, if I make y is equal to 0, in 3D, y is equal to 0 is a plane. In 2D, it's a line, but in 3D, it's a plane. So whereas y is equal to 0, since this is the y-axis, right, and this is positive y, this is negative y is equal to 0, is the xz plane, right? So that's this plane. Got it. All right, there we go. So this is the xz plane, right there, my signature, xz. Royce, no. Okay, that's the xz plane. Got it. Okay, now we know if y is equal to 0, this just says z is equal to x squared. So z is equal to x squared. So the inputs come along the x-axis, otherwise z is equal to x squared is a parabola where the good old y-axis is now represented by the z-axis, and we're on this plane that I drew, right? So it's a parabola contained in this plane, and so it's going to look like this, right? You're welcome for the free three-dimensional graphing within limit lesson. Okay. Okay, there it is. And then of course it's supposed to go through 0, 0, 0. Okay, now if similarly this time I make x equals 0, then in this equation I have z is equal to y squared, right? What's that? And so we see that the parabola z equals y squared has inputs from the y-axis, and the old y-axis is now the z-axis, and the old x-axis is now the y-axis. That's what we're looking at, right? So that's going to look like what? That's going to look something like this, okay? Something like this, right? Okay, so what do we put together as the visual in the end? What I'm going to do is I'm going to keep the axes and show you what the surface would have looked like. The surface, this that we drew two cross sections of, and the cross sections were along the, where were they? Along the ZX plane and then along the ZY plane. Those two cross sections we looked at. But they were parabolic cross sections is the point, right? And so like our solid, well, the surface rather, it's not quite a solid, it's a surface. So it's like the surface of a solid would have been a paraboloid that would have looked like this, right? That's what it would look like. This here is z is equal to x squared plus y squared. Okay, now notice that when we're talking about a limit of xy going to some point AB, so in three of them it's going to 0, 0. I should have written 0, 0 right here. Okay, but yeah, in three of them it's going to 0, 0, and one of them is going to 1, 0. But yeah, basically, since we're on a surface, right, our inputs come from the xy plane, x and y, right? And so if we're considering the limit at a specific point in the xy plane, that could be projected onto the surface. So let's say it's that point. Now, remember, in single variable calculus, well, like what you did is, if you had your input and there was a single input along the x-axis, then in order for you to say the limit is this y value, let's say L, all you had to worry about is coming to A from the left and coming to A from the right. But wait, we're in 3D and our inputs are from a two-dimensional plane. And so that you can come at that from, if this is the point AB, you can approach AB from many different directions. You can approach it along a parabola, right? You can approach it along a parabola, you can approach it along a straight line, and you can approach it along multiple different straight lines. This straight line, the earlier one I drew, so there are infinitely many directions at which you can come to AB. And so the point is that you don't just come from the left and from the right and just check that at the point. You have to come from infinitely many directions. So what happens in practice is, well, you can't do that. You can't exhaustively test all the different directions from which you can come to the point AB. So what you do is you test it from enough directions, and if you keep consistently getting the same limit value, then you do a delta epsilon limit proof to show that the limit is that value that you keep getting despite like changing the direction from which you're coming. Now, important is that you approach the point 0, 0, right? And usually the directions that you should come to a specific point if the limit is going to 0, 0 is, well, that specific point being 0, 0 here, right? So pause. So usually when you're testing for the limits of xy going to 0, 0, these are the directions to follow. Approach it along the y-axis, that's along x equals 0, right? So along x equals 0. And then, and this is approaching it from the y-axis, right? That's when x equals 0, you've got the y-axis. Approach it from y equals 0. So this is along y-axis, and now I have along x-axis. And then approach it from y equals x, so you know what that line looks like, right? Of course, in the xy plane, approach it along y equals x, and approach it also along y equals negative x. Now, if these don't show you that the limit is different as you come to it from these different directions. If these are not enough, then add on to this list y equals x squared, and then y equals negative x squared. Of course, in any given question, you should also use how the curve is defined to gauge which of these is the right one to use, right? Which directions will get you two conflicting limit values. For example, if we pay attention to this one, right? If we approach it along y equals x, you've got x squared minus x in the numerator, plus, and then the denominator. So in the numerator, if we go along y equals x, you've got x squared minus x, because y is equal to x. But in the denominator, you've got x plus x squared. So the numerator and the denominator are different. That's along y equals x. But if we go along y equals negative x, we get x squared, and then minus x, that's x squared plus x. And the denominator will also get x squared plus x. So I kind of already did that question really quickly. But basically I'm saying the way that the curve is defined should also give you clues as to which of these you should approach along. Now, these are usually thorough, right? Like if you go through all of these and you keep getting this same limit value, regardless of which of these curves you're going to 0, 0 from, then you should just say, all right, now let me attempt to write a delta epsilon limit proofs. And as I said, I have many videos on that, so check them out. Oh, Lord Christ, I gotta find my other mask. I'm dying. Okay, all right. Also, just to make the idea clear about this one, I want to do the following really quickly. And this time I'm not going to use a ruler, but visuals, again, help your understanding. So I want to add one more visual. So this is the z-axis. Who needs a ruler? This is the y-axis. If you have any decent short-term memory, this is kind of what we did just now. This is the x-axis, right? Now, consider the following curve. Remember, we already said what, you should remember these guys, write them down in your head. We're going to use them as we go through these, and as I said, I actually did problem 3 already for you, okay, but details to come. Okay, now, here, right, consider the following curve. Z is equal to, you remember what x squared plus y squared looked like, right? This was a paraboloid, right? And it looked like that. Okay, now if we put in parentheses and throw a minus sign, it's going to be a paraboloid, but this time facing down, right? And if we add 1 to it at the end, then these are the same kind of transformations that we learned all those years ago or whatever it is. So here are some cross sections, some slices of our paraboloid. It's going to look like this basically, right? Where this is 0, 0, 1, right? Okay. Now, suppose that AB, the limit point that we're going to, as in this problem, is 1, 0. Then 1, 0 is where x is 1 and then y is 0. So this would be it, 1, 0. Now, so we're going to this point now, right? We're not going to 0, 0 anymore, right? And as we're doing in those 3. So going to 1, 0 along the earlier suggestions, along y equals x, is no good, because y equals x, right? Y equals x goes through 0, 0. So you would completely miss the point that you're supposed to be approaching. So you cannot go along y equals x in the xy plane anymore. So you have to come at it from lines that would actually go through this point. So what are those lines? Well, it would probably be a little bit less mind-bending if we just isolate the xy plane. So if this is x and this is y, we're saying we want to go through this point, right? Like a bunch of things do that. For example, y equals minus x squared plus 1. All right, that does it, right? That would go through that point. So we can approach it along this. We can also approach it along that. What's that? That's equal to y equals, and it's x minus 1, right? And we could also approach it from this direction, and that could be the natural log of x, although that'd be a very exaggerated natural log of x. Or I could do it this way, where it's like y equals root x minus 1. That's a square root function, shifted one to the right. So we can approach it from all these different lines, but the point is that we cannot approach it from the lines and the two parabolas x squared and negative x squared that we wrote down earlier, because those would go through 0, 0, and that's not the point we're approaching in this problem. Yeah? Okay. Breathe. Okay. Now that we've laid the important foundation, let's begin tackling these questions. I've already said everything that needs to be said in order for you to actually do this on your own. The only one where you might need my help is 4, but let's begin as we showed with problem 1. Okay, so in problem 1, this is what we've got. Well, we've got x over y plus x. What does this surface look like? It's kind of weird. Insert. Okay. Alright, so that's what it looks like. And so let's keep to what we said. So we said approach along y equals x and y equals negative x. Yes, we said along x equals 0 and y equals 0, but actually let me do those. We should always begin with those. So let's approach along x equals 0, and there's like a valuable nuanced item that I should discuss with you when approaching along x equals 0 and y equals 0 in expressions like this, because check this out. So when we approach along x equals 0, what we're going to get is 0 over y plus 0. And we say here where y is not equal to 0, right? Because otherwise we get 0 over 0. So where y is not equal to 0, we're going to get that the limit is 0 over y, which is legit 0, right? Okay, so along x equals 0, we see that the limit is equal to 0. Now, here's where I talk about that nuanced item, which involves us saying that y is not equal to 0. Okay, see, we're going to 0, 0. So we're going to x equals 0 and y equals 0. So if we disallow y being 0, does that still make sense? Yes, and the same way as the single variable calculus case, where, you know, if I have that this is 1 and this is 2, both this function, right, both this function and this function, where I've defined the value of 2 somewhere above, both of them have the same limit without this and with this, right? It's the same limit. This limit is x goes to 2 and this visual is 1. I'm saying actually that point doesn't matter. Like the point being defined in the function doesn't matter, so I could exclude y equals 0, and I still can say that it makes sense to approach 0, 0, 0 in this quotient, yeah? Okay, cool, all right. So as we approach along the line x equals 0, and that again is the y-axis, this here goes to 0. But if we approach along y equals x, right? I could approach along y equals 0, but I don't want to do that. That's kind of lame. Actually, let's do it. Along y equals 0, we're going to get x over 0 plus x, which is equal to x over x, which is 1, so long as x is not equal to 0, right? Again, we're allowed this qualifier for the same reason we're allowed the y is not equal to 0 qualifier. Okay, so we see that as we approach along two different lines, x equals 0 and y equals 0, namely, we get two different limit values, 0 and 1. So the limit does not exist. So we go, does not exist. Okay. So we keep it moving. On to the next one. That's that one. And for that one, we're going to x over and then root x squared plus y squared, and we go as xy goes to 0, 0, sorry, why is there an arrow there? Okay, so, alright, so same deal, and since we're approaching 0, 0, the set of guys we wrote here are still good choices, right? So we go, alright, x equals 0, y equals 0, maybe approaching along those, we've graduated from them. So what about if we let y equal x? If we approach 0, 0 along y equals x, then we're going to get x over, and then it's square root of x squared plus x squared. Yes, I could write lim as xy goes to 0, 0. I'm being a little bit casual there because, well, you know, you get it. If you're submitting a problem set for your teacher, then write every detail more carefully. I'm not submitting a problem set. That was many years ago. Okay, and then we've got root 2x squared. So this is x over x root 2, which is 1 over root 2, right? Okay? And so sometimes, other than going to y equals negative x after you've tested y equals x, instead of going to y equals negative x is an automatic. So other than that, useful things to do is like to go y equals mx. And we actually didn't write this earlier, so here it is. So vary m or just use a general m and see what the result is going to be. So here I know setting y equals 2x is a good idea, because in this part I know I'm going to get, instead of simply x squared, I'm going to get 2x squared, which is going to be 4x squared. Once I square 2x squared, it's going to become 4x squared, right? And then here I'm going to have 5x squared. And so I can similarly simplify, but this root 2 is going to turn into root 5. So now we have a different value. We had 1 over root 2 earlier. Now we have 1 over root 5. So no good. Okay, so what do we say? This limit does not exist. Okay, sometimes you could be a little like, what is it, too like casual to a point where like you accidentally offend people even though you don't mean it. So like the breathing on this specific like mask is more difficult than like others, but otherwise I wasn't making fun of the crazy like outrageous situation of like people getting sick all over the world. I hope they all feel better. I hope Jesus goes to their rescue and forgives, like he forgives me and you, like I hope he forgives and has mercy on all of us, but on the people suffering right now. And in fact, I had a student recently who, like, you know, he's one of those kids who's too smart for his own good and likes attention all the time, so like was making fun of the coronavirus, and I reprimanded him in front of class because like, well, it's not funny, right? It's not funny. You shouldn't say anything just to make people laugh. Okay, all right. I just wanted to be clear about that. Okay, and it would be inconsistent of me to like make light of anything serious, given my very strong faith in Christ. Okay, anyway, 3. Okay, so in 3, what could we do? Well, I already told you. So like we're gonna do y equals x, and then we're gonna do y equals negative x. Let's see the same thing that I said earlier, how it makes a difference. So when we go along y equals x, we're gonna get x squared minus x over, and then it's gonna be x plus x squared. So this is going to be x times x minus 1 over x times x plus 1. Then you cancel these x's, right? This one and this one, and this is what you get. Now, as you go to 0, 0, this is going to turn into negative 1 over 1, which is negative 1. This is, again, along y equals x. Along y equals negative x, we're going to have x squared minus a negative x over x plus negative x squared. So this is going to equal x squared plus x over x squared plus x, which is going to equal 1. So we see that this one not in agreement with this negative 1. Okay, and so you know how they say save the best for last? Well, in this case it's really true, but yeah, okay. Here it goes. Can I just tell you, so we save some time, that even if you approached it, first of all, it should go without saying, since I already explained this, that you cannot approach this along y equals x, because y equals x misses the point 1, 0. So you can't do it along y equals negative x, and you can't do it along all the other ones, negative x squared, or along the x-axis, or along the y-axis, or positive x squared. So you can't do it through all of the things that we had done that worked for all of these guys. And by the way, we just said this does not exist, so D and E. Obviously, when the limits exist and they equal a value consistently, as I said, you do delta epsilon limit proofs. And I have many videos on that, so check them out. But here we've got 3 does not exist for a reason, because this is a well-crafted lesson. Okay, but finally, this one, as I said, we cannot use any of those guys. So what we said is we can use these guys. Y equals root x minus 1, or y equals negative x squared plus 1, or y equals, and then it's just x minus 1, right? These kind of things, we can use these. All right, no problemo. You can use all of them, and you'll keep getting the same value. So that was foreshadowing. That was called foreshadowing earlier when I wrote that this is equal to 0. Okay. So, like, you know, basically you suspect that the limit is in fact equal to 0, but you're too lazy to do a delta epsilon limit proof. So how can you attack this? How can you, in other words, evaluate this limit, right, in a more profound way without doing a delta epsilon limit proof? This is what we do, yeah? Okay, what we do is we go, well, let's switch the polar coordinates, and we suspect that that's probably helpful because we've got x squared plus y squared there. But before we switch the polar coordinates, let's turn this 1, 0 into 0, 0. We could do that if we make the substitution that u be equal to x minus 1. With this substitution, now we can write what we have is the same as lim as u comma y go to 0 comma 0. And then, see, because, well, it's x goes to 1, u goes to 1 minus 1, or 0. So u goes to 0, and y, of course, was from the beginning going to 0. But with this substitution, we see that if we solve for x, we're going to get u plus 1 is equal to x. Got it. So, in the numerator, notice that this here, xy minus y is the same as y times x minus 1. And, of course, that would suggest why this substitution might be nice, other than the fact that it would turn this 1 into a 0. And also notice that we could group this denominator, I'm just writing the denominator on its own, as first x squared minus 1 plus y squared, and then next is x plus 1 times x minus 1 plus y squared. So you see x minus 1 show up again. So in the numerator, what we have is uy. Okay, and in the denominator, we just learned that what we have is really u. Now, what's x plus 1? X plus 1 is going to be u plus 2. Because, well, basically, if you take this and add 1 to both sides, on the left, you're going to get u plus 2. On the right, you're going to get x plus 1. So, in the denominator, we've got x plus 1 is u plus 2. So, u plus 2 times what? Times x minus 1 is u. So, times u. And then plus y squared. Yeah, y hasn't changed, so just plus y squared. Got it. Okay. And now the denominator we can simplify as u squared plus 2u plus y squared. Okay, u squared plus 2u plus y squared. Got it. Okay. Now, if you want to, you can go along y equals 0, u equals 0. It's just like y equals 0 and x equals 0 that we talked about at the start, only now you're on the uy axis. So the good old x-axis is turned to the u-axis. And so you can now go along y equals u, y equals negative u, and the other one's important. This is called good teaching. The other important ones that we mentioned, because I'm like basically trying to refamiliarize you, that is, have it in your memory, those nice ones that we said we approach from anytime we're going to 0, 0. Since now we have made sure that we're going to 0, 0, you can use these guys. Okay, but use smarter than that. So, you know, you're going to keep getting 0 as the value and we said we need to show that it is in fact equal to 0 in a stronger case. Okay, now I don't need this, but I suspect that I need the space. So this is what I'm going to do. Well, as I said, we're going to switch the polar coordinates. So we're going to let, since u is the good old x-axis, we're going to let u equal r cosine theta. And then we're going to let y equal r sine theta. Finally, I get to use a different color marker. So now, notice that uy going to 0, 0 means r going to 0. Because if r goes to 0, then u, which is r cosine theta, is going to go to 0. And then y, which is r sine theta, is going to also go to 0. So if we want u and y to go to 0, 0, then we want r to go to 0. That's the proper translation in the limit part. So we go lim, r goes to 0. And then uy is going to be r squared sine theta cosine theta. Now remember, 2 sine theta cosine theta was sine 2 theta. So we can write this as 1/2 sine 2 theta. Got it. Okay, and then in the denominator, we've got u squared is r squared cosine squared theta, and then y squared is r squared sine squared theta. So u squared plus y squared is just going to be r squared by using the fact that sine squared theta plus cosine squared theta is 1. So we've got r squared plus, and then 2u is going to be 2r, and then cosine theta, right? Got it. Now we could factor out 1r from the denominator and get rid of that r right there and turn the r squared into just an r, which means we canceled with an r in the numerator. Now as r goes to 0, we still have an r surviving in the numerator, so we have 0 times 1/2 sine theta. Who cares what the stuff in the parentheses? We have 0 multiplying it. And then in the denominator, we're going to get 0 plus 2 cosine theta. Okay, there's no r there, so the 2 cosine theta survives. So in net, we get 0 over 2 cosine theta, which is equal to 0. This is now the delta epsilon limit proof that that fourth limit was actually, in fact, equal to 0. A delta epsilon limit proof would be the way to go, the more profound way to go. However, this satisfied for now. Okay, I hope you enjoyed this. Keep watching. Take care.